This video is part of my complete practical CCNA course, where I use physical devices to explain and demonstrate topics in the CCNA exam. I think it's really important that you see how things actually work. Real routers and switches, real computers, rather than just learning about this from a theoretical point of view or in a simulated environment. You actually see how things work. In networking, we have what's called the physical topology. That's how devices are physically connected together, as well as a logical topology. Logical topologies, as I'm showing you here, are used a lot in networking. This icon or symbol represents a PC or laptop in this case. Same over here. In this most simple of topologies, we are connecting the two laptops or PCs using an Ethernet cable. If we look at the physical topology, we've got a Windows laptop here. I'll connect a network adapter to the computer, second Windows laptop, connect the network adapter to that one, and plug them in. We now have a network between these two computers. In a logical topology, we can see how data flows through the network. Now, not much happens here. All we're going to be doing is sending traffic or data from one PC to the other. There's nowhere else to go. And this would be a very boring network if you could only talk to one person. So how did they change that? So years ago, they created what was called a bus network. We have networks here called 10 base 5 and 10 base 2. This means speed, as in 10 megabits per second. Please note this is not megabytes per second. A bit is one binary value, so one bit, which could either be a 0 or a 1. Bytes are 8 values. So when we talk about megabytes on a hard drive as an example, or a gigabyte of data, that is different to megabits per second. Baseband means that only one signal can be sent across the cable at any time. So only one person could talk. And this gives us the length of the cable. Now, often I find that when people are shown a bus topology like this, it gets really confusing because all they see is the logical topology that looks like this. How on earth does a PC, as an example, connect to a cable like this and this one connect to a cable like this in a straight line? Doesn't seem to make sense if we think about topologies today. So going back to our network like this, what they did years ago is essentially say, why don't we connect more PCs or devices directly to the cable? And they literally made a hole in the cable. Here's an example of that. This is an example of 10 base 5. And what we do here is we make a hole in the cable and pierce the cable so that we can get access to the network. So any device that needs to access the network is connecting to copper inside of this cable, basically piercing through the outer core to the cable. Now, the way this part was connected from the PC to the network was using what was called a drop cable. Now, you don't have to know the details of this for the CCNA. I just want to explain topologies, like what a bus topology actually looks like. Let's move these Windows laptops away. So here I've got two old computers, a Gateway computer and a Dell computer. How they would connect to the network is using a drop cable like this. You would have to, I know this is a nightmare. Fortunately, they got rid of it. You would have to connect a computer like that to its network interface card, and then you would connect it to the network like this, something like that. And notice that's already clipped out. They had connectors here to stop them clipping out. So you would connect the cable to the transceiver. That would pierce the 10 base 5 or thicknet cable, and you'd have multiple devices doing the same. So this was like one long cable. And where you have black spots like this, that's where you would pierce the cable and connect your devices to the network. Absolute nightmare to work with this cable. There were a lot of problems with this network. Number one, if the cable broke, it destroyed your network. So if that cable broke, this device over here couldn't talk to this device. But what actually made it worse is at the end of these cables, they had to have what were called terminators to stop the signal bouncing back. If you didn't do that or didn't have that, it would destroy your network. So let's say PC 1 over here wants to send traffic to PC 2. What would happen is traffic would be sent to the network through the drop cable. That would be transmitted across the cable. And if there wasn't a terminator here, the signal would bounce back and cause a collision in the network, which would basically destroy the network. Hence, it's called baseband. So 10 base 5. Only one signal can traverse the wire at any given time. Only one person can speak. So there were big issues with this topology. This cable is very, very difficult to work with. Not easy to use, not easy to bend. It's very, very thick, hence called thicknet. If a break happens in the cable, network dies. If the terminators are removed from the end of the network, network dies. Absolute nightmare. devices had to be connected to the network by you making a hole in the cable. Can you imagine this cable in the roof and you having to climb up there, drill holes, and basically stab the cable so that you could get access to the network? Absolute nightmare. Okay, so this is the logical topology, bus network. 10 base 5 was replaced with 10 base 2. This is what that looks like. Much easier to work with cables like this. But the idea here is, once again, it's a bus topology. It's like one long cable. So in this example, I've got the two PCs once again. Notice these connectors here. I've also got a Cisco router here, a very old router, and I could connect a transceiver there. That gives me a 10 base 2 connector. So at the end here, I've got a terminator. This is an example of a 10 base 2 terminator. Bit of a nightmare once again. What you'd have to do is put the terminator on the cable, connect that like that, and connect that over there, and then extend the network by connecting to the T connector. So that's a T connector, and then you would connect it like this. So basically, that's one long cable. Notice here, we don't have the drop cables like we used to have in the old days. We're simply connecting to the PC using a T connector, but it's the same idea. At the end, we have to have terminators. If there's a break in the cable, so as an example, if I disconnected this, it would destroy the network. This device could obviously not talk to these devices, and because there's no terminator, signals would bounce back and basically cause collisions, which would destroy the network. Remember, the concept is this is baseband. Only one device can talk at any given time. If two devices speak, we will have a collision in the network. So the idea is we want devices to communicate. We could connect them directly, but if we wanted to extend the network, we could connect them using a bus topology. Not such a great way of doing it. This, once again, is the physical topology. This is actually how it looks. This is a logical topology. In my example here, we haven't got as many devices. We've only got PC1, PC2, and then this would be a Cisco router. So we've only got 3 devices. That's our physical topology. Here's our logical topology. Fortunately, we got rid of 10 base 5 and 10 base 2, and we replaced it with UTP, or unshielded twisted pair. So this stuff is no longer used today. You're going to come across various types of Ethernet cables. Here's an example of flat UTP. So much easier to work with this cable than these cables or 10 base 5. But you always need to remember the difference between the logical topology and a physical topology. So we got rid of 10 base 2 and 10 base 5, and we replaced it with 10 base T. Unshielded twisted pair cabling looks like this. You might see different variations of it, but the important thing to note is at the ends we have RJ45 connectors. There's actually another name for these connectors, but if you work in networking and the real world, people will refer to these as RJ45 connectors. The topology changed as well to a star topology. So rather than one long cable, we now connect to a hub. Here's an example of an Ethernet hub. This is not a switch, this is a hub. And what we would do is connect our devices using UTP cabling like this. So different cables could be used to connect to different devices in the network, all connected to a central device, hence the term star topology. So this is a star topology because we have the central device and then we have stars coming out or radiating out of that central device. And our PCs are connected to the star using an individual cable like this. The advantage of that is, let's say this blue cable has a break in it, so something goes wrong with this blue cable, it doesn't affect the gray and black cables. Whereas when it was a bus topology, if there was a break anywhere in the cable, the entire network would break. Now, you need to be careful with what a physical network looks like versus a logical network. Notice here, just to show you some more examples, we've got another Netgear hub here with many more ports. Here's a Cisco Fast Hub 400 series. These are hubs at the top. They're not switches. These devices at the bottom are switches, and I'll talk about switches in a moment. And the difference between these are hubs that allow us to build a star topology. That's what it looks like physically, if you like. But logically, it's actually a bus topology. So traffic actually flows like this, in that when one device sends traffic, it's sent to all devices in the network. The reason for that is if traffic is sent on one port, let's say I have a PC connected to this port on the hub. When traffic arrives from this Windows computer, let's say, traffic is sent along the cable to the hub, and that traffic is replicated out of all other ports except the port on which it was received. So if I had 20 other devices, let's say, connected to this 24-port hub, all 20 devices would receive the traffic because traffic that arrives on one port is flooded, is the term, or replicated out of all other ports. This is known as a multi-port repeater. This device is a dumb device. It doesn't understand the traffic that it's receiving. It doesn't realize which MAC address the traffic is going to. It just simply replicates it out of all ports. Hence, a multi-port repeater. We have multiple ports, multi-port, and we just repeat the signal out of all other ports except the port in which it arrives. From a collision point of view, this is a problem because let's say PC1 in our topology sends traffic to PC2. So traffic is sent to the network. But at the same time, PC5 over here also sends traffic to PC3. That traffic will be sent across the logical cable and there will be a collision here. And when there's a collision, all devices on a bus network or on a hub network like this have a random back-off timer. So they randomly back off and then try again. This is known as carrier sense multiple access collision detection. They will detect when there's a collision. Carrier sense says that before they transmit traffic onto the network or data onto the network, they should listen to make sure that no one else is speaking. Multiple devices can access the network at any time. In other words, multi-access. There isn't a central device controlling who can speak. That's different, for instance, to a token ring network. And here's an example of a token ring switch, where a device can only send traffic when it has a token. This is known as a ring topology. Physically, it doesn't look like a ring, but logically, it is a ring topology. But as you can see over here, hopefully, it says Smart Desk Stream Token Ring Switch. This is totally different to Ethernet. It's token ring, not Ethernet. Or in a mainframe environment, the main device or mainframe controls who can talk. That's different in Ethernet. Anyone can talk at any time, but before they talk, they need to make sure that no one else is speaking. But let's say both PC1 over here and PC5 speak at the same time. They both check to see if anyone is speaking. At the moment, no one is, so they both transmit traffic at the same time. Traffic is sent across the network and there's a collision. Then we have collision detection and the devices back off and then try again later. Now, sometimes when I show topologies like this and explain some of this technology, people tell me no one uses hubs today. But you need to understand this kind of technology because Wi-Fi acts in many ways like a hub. But Wi-Fi devices are still sharing the same spectrum. And if you have a lot of devices on your Wi-Fi, it will slow things down. So in a bus topology and a hub topology, we have 10 megabits per second. That's the speed. But this is actually shared between all the devices. And it actually gets worse. So if you have 5 devices like here, in theory, 2 megabits per second is what you get. But because of collisions, you actually only get about 30% utilization. So it's 10 megabits per second times 30%, let's say 3 megabits per second, shared by the number of devices. So divide that by 5. You get very little bandwidth. So 10 base 2, 10 base 5 wasn't great. Hubs weren't great because even though it's a star topology, we have all the devices connecting to a central device like this. Logically, it still acts like a bus where collisions take place. It's a shared medium. So if we even had 100 megabits per second hub here, you're still only getting about 30% utilization. All the bandwidth is shared between all the devices. So it's 100 meg shared between the devices, not 100 megabits per second each. This is known as a single collision domain because a collision anywhere affects the entire network. If PC1 sends a message to PC2 and 3 sends a message to 5 and a collision takes place and 5 sends a message to 3, collision here affects everyone. Single collision domain. It's also known as a single broadcast domain because a broadcast sent by any device is received by everyone else. Single broadcast domain. In networking, we have what are called unicasts, broadcasts, and multicasts. A unicast is one-to-one communication, so one device talking to one device. A broadcast is one device talking to everyone. So when a broadcast is sent onto the network, who receives it? I'll get into the details in a separate video, but basically it's a message going to everyone. A multicast is a message sent to a subgroup of people. So as an analogy, think of email. When I send an email to you, that's a unicast, one person talking to one person or one device talking to one device. A broadcast would be a message sent to the entire company, so an email sent to everyone in the entire company. A multicast is like where you subscribe to an email newsletter. So only some people receive the email. Not everyone receives the message. When PC1 over here sends a broadcast, that's received by everyone in the network. This is a single broadcast domain, single collision domain and single broadcast domain. Now, just like with a bus topology, this is a single collision domain. If PC1 sends traffic to PC4 and at the same time PC2 sends traffic to PC6, a collision is going to take place, and that affects the entire network. Remember, this looks like a star but acts like a bus. This is also a single broadcast domain because a broadcast sent by any one device is received by all the other devices in the topology. Again, this looks like a star but acts like a bus network. Broadcast, unicast, doesn't matter, multicast is sent to everyone in the topology because when a hub receives traffic on one port, it replicates the traffic out of all other ports. Single collision domain, single broadcast domain. Not great. Now, after hubs, bridges were developed, and this really changed networking. Here's an example of a bridge. Switches are very similar to bridges in that they learn where MAC addresses are in the topology. There are differences between a bridge and a switch, and I'll talk about that right now. But first, I want to show you that bridges actually existed. This is a physical bridge. People sometimes complain that I show older devices in my videos, but understand that even today, in a very modern switch like this, a 9200 series switch, it still refers to a root bridge in spanning tree. So you'll see the term bridge in spanning tree, and that's because spanning tree ran on a bridge like this. Bridges and switches learn where devices are in the topology. They learn the MAC addresses of devices and only forward traffic out of specific ports based on where the MAC address is. Huge improvement in networks. Some differences between bridges and switches is bridges do things in software, switches do things in hardware. They have what are called application-specific integrated circuits, or ASICs, allows them to move traffic very, very quickly in hardware rather than using a central CPU. On some switches, traffic can be moved from one port to another using chips directly on the ports rather than going to a central processing unit. Whereas on a bridge, it was done in software. Everything had to be done by a central CPU. There are also fewer ports on a bridge. So as an example, notice this bridge only has 2 ports, whereas this switch has 24 ports. So you'll get 24 port 48 and switches with many, many more ports today. More ports on switches works with hardware. Bridges, fewer ports, uses software. They both, however, use MAC addresses to discover where devices are and then forward traffic according to the MAC addresses that have been discovered. That reduces the collisions in our network and gives us greater throughput. So if PC1 sends traffic to PC4 as an example, let's assume the MAC address of PC1 is A, MAC address of PC4 is B. MAC addresses are 48 bits in length, written hexadecimal. I'll just keep it very simple here. PC1 sends traffic to PC4. The bridge will learn where the MAC addresses are of the devices. Initially, it will flood the traffic out of all ports until PC4 replies and the bridge learns where the device is. But once it's learnt where devices are, all traffic sent from PC1 to PC4 is only sent out of this port. Let's assume it's port 1, 2, 3, 4, 5, and 6. Traffic is only sent out of port 4. PC5, PC6, PC2, and PC3 do not see the traffic sent from PC1 to PC4 because the bridge has a MAC address table and has learnt that A is on port 1 and B, the MAC address of PC4, is on port 4. And excuse my bad handwriting. Hopefully that makes sense. At the end of the day, traffic is sent directly to that device. When PC3 sends traffic to PC6, once the MAC address table is updated, that traffic is forwarded directly between those 2 devices without interfering with others, and the same is true for PC1 and PC4. So in a topology like this, if a collision takes place, it doesn't affect the entire network. And we actually have here 1, 2, 3, 4, 5, 6 collision domains. It is, however, a single broadcast domain because if a PC sends a broadcast, that's received by everyone in the topology. So 6 collision domains, a single broadcast domain. Now switches are very much the same as bridges. In a topology like this, we have 1, 2, 3, 4, 5, 6 collision domains. A collision on a link here only affects that link, doesn't affect the other links because the switch, just like a bridge, learns where everyone is in the topology and only forwards traffic out of certain ports. If traffic is sent from PC1 to PC4, just like a bridge, the traffic is only sent out of the relevant port once the MAC address table is populated. We'll talk about that in a lot more detail later, but basically the switch will learn that A is on port 1, B is on port 4 in a topology like this, and will only forward traffic out of the relevant ports. When traffic is sent from PC4 to PC1, it'll only be sent out of port 1 because the switch has learned where devices are in the topology. But just like with a bridge, this is a single broadcast domain. If a broadcast is sent into the topology, all devices in the network receive that traffic. So every device here will receive the broadcast. The broadcast is sent out of all ports except the port in which it's received. So this network consists of a single broadcast domain and 6 collision domains. I'll be showing you that practically in more detail later so that you can actually see how the traffic flows in the topology. For now, just try and get an understanding of how this works. A big advantage of switches and why we use them is they give us many ports. In other words, we can connect many devices to the network. You get different sized switches. So as an example, this switch only has 8 ports. This switch has 24 ports as an example. Again, you get switches with many, many more ports. But these switches at the top are examples of unmanaged switches. These are managed switches. Unmanaged switches tend to be a lot cheaper than managed switches, but you can't change the configuration of the switch. You get it as it was made by the manufacturer. This is an example of a Cisco switch. This is a TP-Link switch. You simply plug in your devices. The MAC address table of the switch is populated and it learns where devices are in the topology, but you can't change anything. But works a lot better than a hub or previous technologies. With managed switches tend to be more expensive, but give you the option to configure them. You can change the configuration of a managed switch. So as an example, you could, and we'll talk about this later, create what are called VLANs or virtual local area networks, where you stop broadcasts from going through the entire switch. So you could say, these ports belong to one VLAN, these ports belong to another VLAN. Broadcasts sent on these ports stay here. They don't go out of these ports. Don't worry too much about that. Lots to cover. Moral of the story is managed switches allow you to change the configuration of the switch to give you better security, to manage traffic better. Unmanaged switches, you get what the manufacturer has given you. You can't change the configuration, but give you ports so that you can expand the size of your network. Now, routers do many things, but one of their most important jobs is to connect our local network to other networks. The whole idea with networking is that we can talk to other devices. Not just our local network. We want to get information from YouTube, as an example, watch YouTube videos, or we want to read the news. We want to get information from other networks. So in a topology like this, we have a router that connects us to the internet, and the way that that connection is done can be different. As an example, something that's become really popular recently is Starlink. On the Starlink router, I have an Ethernet connector. So I could connect my laptop, as an example, to this connector. So this is connected to the satellite dish and to the Starlink router. But you may want to connect this to an Ethernet switch, such as this switch, to give you more ports. So rather than connecting to the Starlink router using just Wi-Fi, you could connect to the Starlink router using Ethernet in a similar way to what I've shown here. So as an example, this could be our Starlink router. This is the internet. We're accessing that through satellites. So here's an example. I've got the satellite dish that would connect us to the internet via satellites. And on this side, we've got an Ethernet connection to our switch. And then we can connect multiple PCs to the Starlink router. We could do that using Wi-Fi, but you may want to run multiple access points or more devices using Ethernet, and that's what this gives you. So that's very typical of a home network. You may have something similar at home where you have your PCs connected directly to a switch or directly to a router that connects you to the internet using something, which could be, as an example, satellites. It could be 5G. This is a 5G router. Here's a Cisco 4G router. So in the same way, I could connect my switch to this router on the LAN port or local area network port. Allows me to connect the 5G router to a switch that gives me many, many ports. And then the way I get to the internet in this case is 5G. Or on the Cisco router, as an example, it has some built-in Ethernet ports. I could expand that with a switch, and this connects me to 4G. So this is a 4G Cisco router. Or in this example, with this Cisco router, it has an Ethernet WAN port. So in that case, you may be connecting to fiber. You might have fiber to your home, as an example. Or on this router here, it has a DSL port. So you'd connect a telephone cable here. So you'd get access to the internet using ADSL as an example. This is an 8200 series Cisco router, much bigger router. And once again, the way that we're going to get to the internet is via Ethernet. So this would need to connect to a modem that provides fiber as an example. So the basic idea here is my router allows my local area network or LAN to connect to the WAN or wide area network using some kind of technology. It could be Starlink, it could be 5G, it could be fiber, it could be a telephone line. There are lots of options, and in the old days, we used to use serial links as an example, or leased lines. So you may still come across that in your studies or in the real world. Serial links have been replaced in many cases with Ethernet and other technologies. Now, a company may have many sites. Here's an example with just 2 sites. We've got PCs connected to a switch, say switch 1, which in turn is connected to router 1, which in turn is connected to the internet. Here's another site. We've got router 2, switch 2, and some PCs. The idea here is traffic is routed from one network to another. So routers route us from our network, for instance, to the internet. And the internet is made up of many routers. Many routers in the internet with lots and lots of routes. But the idea here is we are routing from our local network to the WAN. And on this side, we're routing from the WAN to the LAN. So we've got a LAN this side, we've got the WAN or wide area network, and on this side, we've got another LAN. Now, from a traffic point of view, important to note that each interface on a router is a separate broadcast domain. If broadcasts are sent by any of these devices, the router will not forward the broadcast onto the internet. And in the same way, if a broadcast is received by router 2 on this interface, that broadcast is not forwarded to the local area network. Every interface that's a routed interface on a router is a separate broadcast domain as well as a separate collision domain. Now, the world these days is kind of blurred. Here's an example of a home router running ADSL and some Ethernet ports. One of them is actually marked as LAN WAN and the others are LAN. This is a router, but it acts like an access point with Wi-Fi. It acts like a switch in some ways because traffic on the LAN is switched between ports, but then routed to the WAN interface, let's say this interface. On a Cisco router, something similar could be done. On this router, these are switched interfaces, and these would be routed interfaces. So depending on the router, and it also depends on the switch, some interfaces can act like a routed interface and some interfaces can act like a switched interface. Router interfaces stop broadcasts. Switched interfaces will forward broadcasts. What is this device? This is a firewall, or as Cisco call them these days, a Cisco Secure Firewall. This specific device is a Cisco Firepower 1010, a little firewall, but notice it's got some switch ports on it that allows you to connect to the internet using an Ethernet connection. Firewalls essentially protect us from bad actors or bad people trying to hack into our network. Now, in a home environment, as an example, you may have a little router like this. And again, this is what gets confusing about home routers like this. They combine lots of functionality. This typically has a built-in firewall, but how good that is really up to debate. It's a router, it's an access point, it's a switch, and it's also a firewall. Now, this may be okay for some home users, but in an enterprise or larger business, you're going to want to have a dedicated firewall. And this obviously is a very small firewall in a small or medium-sized business or branch office. Very small firewall. Cisco have much larger firewalls than this for large enterprises. A device like this these days has a lot of intelligence built into it. You can do simple things where you say traffic is allowed from your inside network, so your secure LAN, to the WAN or the internet, but traffic is not permitted from the internet to the LAN unless it's an answer to traffic from the LAN to the internet, or what we called the inside interface and the outside interface. So in a network like this, you may have some PCs connected to a switch, which in turn is connected to a router, which has a firewall in front of it that connects you to the internet. Now, this is possible if you, for instance, got fiber to the office or your home, and you are connecting the firewall via Ethernet to your modem or device that your ISP is installing at your premises. Now, that's not always possible because this connection could be something else than Ethernet. What happens if this is ADSL or some other type of technology? Maybe using Starlink, or what about 5G, something else for this connection? In that case, the firewall is connected to the router and the router connects you to the internet. So again, this could be a 5G router, this could be a Starlink router. Some kind of router is used here that gives you physical connectivity to the internet, and your firewall is behind your router. So traffic arrives from the internet, as an example, is sent to the firewall, is permitted or denied to your internal network. This may be your outside interface, and this may be your inside interface. And you may also have something here like a third interface, which is your DMZ, where you have servers or other devices that people can access through the firewall. The physical installation of firewall behind router or firewall in front of the router really depends on what kind of internet connection you have and whether you want the router to be in front of the firewall or the firewall in front of the router. So it's really up to you how you decide to install this, but a big determining factor is what type of connection do you have to the internet. This couldn't connect to Starlink directly. You'd have to connect this to a Starlink router, which connects you to the satellites and the internet. Now, one of the features that a firewall may have is something called IDS, or Intrusion Detection System, or IPS, or Intrusion Protection System. So IDS or IPS basically allows us to detect bad guys or bad traffic and then do something about it. And I'll give you an analogy that will hopefully help you remember the difference between the two. Think of an IDS as a small dog. You're sleeping at night, sound asleep, and suddenly someone decides to break in. So there's an intruder in your house. What does a small dog do? It sniffs that there's an intruder, and then it barks. In other words, it alerts you that there's an intruder. So it's an intrusion detection system. The dog detects that there's an intruder and then notifies you or alerts you that there's an intruder, and then you can do something about it. An IDS running in a firewall will detect that there's malicious activity on your network and then will alert you, and you need to do something about it. Think of an IPS, or intrusion protection system, as a very large dog compared to an IDS, which is a small dog. An IPS, intrusion protection system, goes a step further. You're sleeping at night. An intruder breaks in. The dog, in this case a very large dog, doesn't just alert you by barking that there's a intrusion, but it also protects you by attacking the intruder. So an example with a firewall would be traffic is going through the firewall. With an IPS, traffic has to go through the IPS system. So the traffic is going through the firewall and the IPS system. When there's an attack, it blocks the attack, so stops it. Whereas an IDS is normally sitting out of band. It's not in the flow of traffic. It's sitting next to it. It gets copies of the traffic and can only alert you that there's a problem. It can't stop the attack. So IPS will stop the attack, and IDS will just alert you that there's an attack, and you'd have to do something about it. So hopefully that helps you. IDS, small dog, IPS, large dog. Now, many of our devices, such as laptops, MacBooks, and phones, don't have Ethernet connectivity. In other words, we are not going to physically connect the laptop or the phone to the network. What we're going to use is Wi-Fi. And I think for most of us, we know what Wi-Fi is. In our home environment, once again, with a little router like this, we'll be connecting to the Wi-Fi router. It'll be taking the signal from Wi-Fi to Ethernet to get us onto the internet and back again, or whatever your WAN connection is. But the idea here is that we are connecting through the air to the network. But at some point, that's going to go through a wired connection, which could be copper, could be fiber, could be something else. Now, these are access points that I'm going to use in the course. From a Cisco point of view, you have what are called autonomous access points and lightweight access points. An autonomous access point basically is configured by itself. It has its own brain, if you like. So this access point would be configured individually. I would connect to it using a web browser as an example and then configure the access point. But if I had many access points, rather than just 1 or 3, but let's say 50 or 100 or 500 access points, it's going to be a lot of work to individually configure those access points. So in that case, I want to use what's called a lightweight access point. These are actually lightweight access points. They can function as autonomous access points. But in this example, we are going to use a wireless LAN controller to configure those access points. So rather than configuring, let's say, 100 access points individually or 500 access points individually, we are going to configure them through a controller. We're going to use a wireless LAN controller to configure the devices. So in that case, we would connect it to an Ethernet switch such as this one, and then power over Ethernet would be used to power these access points. You don't really want to be going into the ceiling and run power cables to your access points to configure them. You'd rather have them powered through the Ethernet cable. So a switch would provide PoE, or power over Ethernet, to the access point. That powers the access point, but also allows Ethernet connectivity between the access point and the switch and to the controller. So in this course, I'll show you how to set up the WLC or wireless LAN controller so that you can configure the access points. You need to know Wi-Fi for the CCNA exam. It's one area where people seem to really struggle. So I'm going to spend a lot of time showing you how to set this up, and then you can configure it in Packet Tracer as an example. The problem with Packet Tracer is, again, it has some limitations and doesn't set this up properly. So I want to show you with a physical device how it actually works. So in our topology, once again, we've got PCs connected via Wi-Fi to the access point, and the access point is taking the transmission and sending it on the Ethernet network to the internet. So here we've got Wi-Fi, here we've got Ethernet between the access point and the switch, and then between the switch and the router, we'd be using Ethernet typically. And then this could be fiber, it could be Starlink, it could be 5G, or some other technology that gets you to the internet. I think that's understandable for a lot of us. We are connecting using a Wi-Fi device such as a phone to the access point. In this case, it's a router that has an access point built into it. Takes us to the internet using a WAN connection, or we can connect to local devices using the LAN connections. So again, in our topology, here we could have another PC, excuse my bad drawings, but let's say this is a PC, and traffic is going through Wi-Fi to the PC that's wired and then going back again.